Okay, we continue on to binary variables. And binary variables are those that can only take on two integer values, either is 0 or 1. So the first problem that we look at is also in our Ragsdale textbook. So this is the problem where there are six projects to choose from, and each project varies in net present value, the future cash flow discounted to the present value in total, and then each project require different capital investment in each year, and we're looking at 5 years ahead. So the objective is to decide which project to invest, to select, and then okay, so the company is limited by the cash available for investment. So 250 in total, and 250 is split into seven. Okay, 250 in year one, and then 75K for year two, and 50K for year three, four, and five each. And then so to make the problem easier, surplus funds in any year cannot be moved to the next year, so it's going to be used for something else. So we yeah, so we have to define again decision variables. So our oh x xi is 1 if project I is selected, chosen, and 0 if it's not selected. And we have I from 1 to up to 6. Okay, and so the model is we want to maximize. Oh wait, hold on. We want to maximize total NPV. So we want to maximize total NPV, and our constraint is that subject to total cash, total capital needed cannot exceed the budget, yearly budget. Oh, total capitals needed in year J cannot exceed the yearly budget of year J. Okay, so we can, and then we also have the constraint on the binary decision variable. So xi can be either 0 or 1. So these are binary constraint. So yeah, so this is the Excel model of the project selection. So these are our decision variable: x1, x2, x3, x4, and x5, and x6. And the objective value is here. So first, we put in the formulas for capital required each year, and total net present value. So we just do sum product of xi's and then the total NPV. Okay, and so essentially we did 141 x1 plus 187 x2 and so on. And then for the capital required, the formula is similar. So we just do some product of the decision variables with the capital required each year, because the decision variables column B is going to be used again and again in year 2, 3, 4, and 5. So I'll just fix the formula. And then I can copy them out.
And then I'll call up the Excel solver, data solver, and then I want to objective is this one, and I want to maximize. Changing variable cells are these six, and then the constraint is that the capitals needed cannot exceed what is available. And then I also need to have the constraint being binary, so it's been here. Okay, and so again, the objective is to maximize total net present value, and decision variables are these, and then capital required in row 12 cannot exceed the amount available in row 13. And we click solve. So we can see that the optimal solution is to select project 1, 4, and 5, and then with the total NPV of 489. And then, I mean, if you want to, you can just redo the problem using another solver here. You can use another solver as well, but I'm not going to do it.
So, binary decision variables, the ones that can take only the values of 0, 1, are also useful in modeling a number of logical conditions. For example, in the same problem of project selection above, we can add the conditions like of projects 1, 3, and 6, no more than one may be selected. So the sum of these variables cannot exceed 1, so no more than 1. Then it becomes this. And of projects 1, 3, and 6, exactly 1 must be selected. So x1 plus x3 plus x6 equal to 1. And the project 4 cannot be selected unless project 5 is also selected. So if x4 is selected, if it's 1, then x5 is automatically 1. But if x4 is 0, then x5 can be either 0 or 1. Okay. And then we can have so this is similar to the case below. If item I is selected, then item j is also selected. So if xi is 1, then xj is forced to be 1 because all these variables are binary. But if xi is 0, then xj can be either 0 or 1. And then either item I is selected or item j is selected, but not both. So either one of them is 1. And then if item I is selected or item J is selected or both, so yeah, we can have like if they are selected, either one of them may be 1 or both of them may be 1. If item I is selected, then item J is not selected. This might be easier to see if you look it um, like negatively, like xi less than or equal to 1 minus xj. So if item I is selected, then item j is not selected. And then if item I is not selected, then item j is not selected. So if item I is 0, xi is 0, then xj is automatically 0. And then we can have more than two items, like at most one of items I, j, k are selected. So we can have xi plus xj plus xk at most 1 less than or equal to 1. At most one item. At most 1, so it's less than or equal to 1. And then at most 2, similarly, we have like instead of less than or equal to 1, then become less than or equal to 2. And then at exactly 1, exactly one, exactly one, and then at least one, at least one. Okay. And so, like, if we go back to the item selection problem or the knapsack problem above, we have something like maximize total values such that the cost do not exceed 14, and xj represents the decision whether or not we select it or not select it. Okay. And suppose we can add conditions, like suppose that I refuse to select item 5 if I have also selected item 1. The feasible solution will permit x1 equal to 1 or x5 equal to 1 but not both. So we can have it mathematically like this. And then I will take item 3 if and only if I take item 4 too. So if and only if is essentially like equal. So x3 equals to x4, or we can write it as x3 minus x4 equal to 0. Sorry. And then I choose exactly 3 items. So the sum of all the x's equal to 3. Okay, just to continue on the transforming the logical constraints. Now we have the either or conditions. So we have either 2x1 plus x2 is at least 5, or 2x3 minus x4 less than or equal to 2, or both. So we can call the first statement to be statement A, and this is statement B, logical statement B. So for the statement or, so either one of them just have to be true, and the whole statement is true. But if both of them are false, then the whole statement is false. So here we are not assuming that xi is binary. In fact, we are not even assuming that it is required to be integer value. But for our transformation to work, we do need to require it to be bounded. So we assume that x1 and x2 are less than or equal to 100 for each of them. So let m be a constant that is large enough in this case, because we assume that xi is less than 100, so we can choose m to be twice as large. So we're going to choose m to be 200. So the first statement becomes 2x1 plus x2 greater than or equal to 5 minus a large number m times a binary decision variable y1. And the second statement becomes 2x3 minus x4 less than or equal to 2 plus m times 1 minus y1. So now we have these two statements, and then let's look. So if y1 is 0, then statement if y1 is 0, then statement A is true, and B can be either because statement B becomes 2x3 minus x4 less than or equal to 2 plus m. So B can either be true or false. But if y1 is 1, then the second statement, the statement B, is true, and A can be either true or false. So now this logical statement becomes these two inequalities, and also we introducing a new binary decision variables y1. And then yeah, so just to summarize, if we have greater than or equal to or greater than sign, we use a minus to decrease the lower bound further. But if we have less than or equal to or less than, we use plus to increase the upper bound. And then so we will have m times y1 on one equation, and times 1 minus y1 in the other ones. So this one, I mean, the sign matters, but the order in which we place these two doesn't matter. So just to summarize, so these logical or becomes these two inequalities with a new binary decision variables. And with this, we can transform an if then constraint. So if we have a statement, if A then B, if A then B, then it's equivalent to not A or B. Okay. So we can write not A as like 2x1 plus x2 larger than 5, and then or statement B remains the same. So we can apply what we have learned up there. So we just do so it's greater than, so we do apply, so greater than we use minus to decrease the lower bound. And then the second statement, because it's greater than or equal to, we use the minus, greater than or equal to, we use a minus sign again for, but then the other one is m times 1 minus y1, and then we declare y1 to be binary.